Heat is the thermal energy that is moving. Now this is the thing, is heat is a type of energy, a form of energy. Heat flows at any time there's a difference in temperature. So look at the example. What makes the chocolate melt in your hand? Okay. Well, we know that your hand is warm. And the chocolate, to begin with, is at room temperature. But what happens is there is a difference in the temperature. So heat flows from hot to cold. So from high to low. Okay. Where there's high heat energy to low heat energy. So because your hand has more thermal energy than chocolate, the thermal energy flows from your hand to the chocolate, and the chocolate begins to melt. This is the case also when you hold a glass of cold water or cold lemonade, your hand feels cold. But it's not the ice that is making your hand feel cold. It is the heat leaving your hand, making your hand feel cold because it's transferring from your hand to the cold glass. So from high to low, from hot to cold. Heat and temperature are not related, but are related, but are not the same thing. The amount of thermal energy depends on the temperature, but it also depends on the amount of matter you have. Okay. So when we're looking at temperature, temperature is the amount of energy per molecule. So when you are actually taking the temperature of something, putting a thermometer in it, you are measuring the movement of the molecules. You're not actually measuring the energy, you're measuring the movement, the kinetic energy of it. So the amount of thermal energy depends on the temperature, but it also depends on the amount of matter you have. So temperature is related to the random motion of molecules in a substance. The higher the temperature of a substance, the faster is the motion of the molecules. So here in this example, you have 1,000 grams in this pot, and you have 2,000 grams in this pot. Obviously, there's 1,000 grams more in this one. They are both, though, at 100 degrees Celsius. But because the 2,000 grams has more matter, so it's the amount, it has more thermal energy than the 1,000 grams, even though they're the same temperature. Now, if I have a cup of coffee, and that's very hot coffee, and if I have a big bucket of warm water, now here the temperature is different. It's hot here and it's only warm over here. Even though there's a size difference, amount difference, because the temperature is higher over here, it means it has more thermal energy. Okay. Again, another example. Here, the total potential and kinetic energy of all particles in an object depends on the mass, temperature, and phase of an object. So here we have another example, 200 milliliters versus 400 milliliters. Again, same temperature. Okay. Now, we talked about the mass and the temperature difference. Now, phases. If you have a solid, a liquid, and a gas. We know that a solid has particles that are very, very close together and are moving very slowly. Whereas liquids, their particles are a little bit farther apart, moving a little bit faster. Gases are even farther apart because they are moving faster than liquids. So we have them as a gas, a vapor, so to speak. So because gases are moving quicker, they have more thermal energy. Liquids, not as much. Solids, very little. Now remember, solids aren't stop moving. They're just moving so little that there's no obvious motion of the movement. Now measuring heat and thermal energy. And this is a review because we measured joules when we talked about kinetic and potential energy, because we use this for heat, but it is also the same joule used for all forms of energy, not just heat. So you'll see joules used. You'll also see calories and BTUs used to measure heat, depending upon what you're referencing. Joule is a typical common one that you're going to see used. You'll see calorie used. It tends to go along with food. Calorie is the measure of amount of heat energy contained in basically chemical bonds. So here it shows you that 1 gram of water at 10 degrees Celsius. So you add 1 calorie of heat, it increases the temperature by 1 degree Celsius. So that is the measure of a calorie. They determine a calorie in measuring food by burning it. And they measure the amount of energy that's released as heat. And that's what they determine is the calorie. So if you take a peanut, an individual nut, like a little Planters peanut, you're going to eat it. It says that this is 10 calories. And they tend to say food calories are used with the capital C. Okay. This means that it releases 10,000 little calories. And I call them little calories because they reference it using a lowercase c. Okay. Or that is equivalent to 41,860 joules of energy. Meaning that's the amount of energy that is released when this nut is burned or digested. Okay, so once that energy is released, your body can use that as energy right away. And if it doesn't use it right away, what is it going to do? It turns it to a reserve that we have in our body. That's fat. So that's why they say you are limited to about a 2,000 calorie diet, depending on your age and your activity level. Your amount of calories will differ. But if you consume more calories than what your body actually uses, it takes that and converts it to fat because the energy released from that food is not going to be used, so your body saves it for a later time. A BTU is called a British thermal unit. This is referencing basically things that are combustible. It's a measure of heat by burning any material. So combustible means that it's being able to be burnt. So combustible materials. Some of the combustible materials that we're familiar with is propane. Propane is rated at 15,000 BTUs. Charcoal is 9,000. And wood at 7,000. Now, when they're talking about grills, you go to the store and you buy a new barbecue grill, and they have, this is a 35,000 BTU grill, and this one's only a 15,000 BTU grill. That is not actually measuring the heat output. That is just telling you the fuel usage. So people are going to go, oh, I'm going to blow through my propane tank a lot quicker if the higher the BTUs it is. The lower the so depending on how many BTUs your grill is going to use determines how much propane it's going to be using. And notice that the BTUs is measured similar to the calories, but here they reference 1 pound of water. And it's still at a 1 degree Celsius increase. So it's BTUs of heat. So you're adding the heat to increase the pound of water by 1 degree Celsius versus a calorie. So very similar, depending on what your reference is on talking about that. Thermal energy is often measured in calories. Here we are just explaining verbally what it actually means by increasing the temperature 1 degree Celsius of 1 milliliter of water. Specific heat. Specific heat is a property of a substance that tells us how much heat is needed to raise the temperature of 1 kilogram of a material by 1 degree Celsius. This is kind of like a trademark to specific things. Every material has its own specific heat, so you can kind of gauge of what it is. Knowing the specific heat of a material tells you how quickly the temperature will change as it gains or loses energy. So the higher the specific heat, the longer it takes to lose or gain the energy. So gold is only 129. Means it's going to heat up very, very quickly, but it's also going to cool down very quickly. Water, on the other hand, takes a long time to heat up. You ever try to boil water to make macaroni and cheese? It seems like it takes forever for the water to start to boil. That's because it takes a lot of energy to raise the water 1 degree Celsius to get to the boiling point. Okay. You'll notice that water is unique and is used for different things. You can take water and you add it to different things you cook. You can put it into a cupcake baking cup. And the paper on the baking cup doesn't burn, but the cupcake mix cooks. That's because it contains water. It contains something that has a high specific heat, so the energy is absorbed there versus the paper. Same reason why you can put out birthday candles using licking your fingers. That's why firemen use water to put out fires, because it doesn't heat up very quickly. But this is also one of the reasons why living next to the lake, we get the lake effect snow. Because when the air temperature gets cold, the water doesn't get cold because it takes a long time for it to cool down. So it doesn't freeze right away, so it still evaporates into the air, giving us lots of snow early in the season and then again late in the season. And when it's frozen, that's when we have a period of no snow. Okay. So liquids have different specific heats, but so do solids. Aluminum. We're very familiar with aluminum foil that you use when you cook. You can cover your dish, bake it at 350 degrees, pull it out of the oven. A couple seconds later, you can touch it and take it off the top and it doesn't burn. That's because it has a low specific heat. Now we know glass heats up quickly because it has a low specific heat, but it also cools down quickly. Think about the different containers that you have in your house when you put your drinks in them, how they will transfer the heat and quicker than some than others. Specific heat is different for different materials. Temperature measures the average kinetic energy per particle. Energy that is divided between fewer particles mean more energy per particle. So you don't have to share as much for as many, and therefore more temperature change. In general, materials made up of heavy atoms or molecules have low specific heats compared with materials made up of lighter ones. On the next slide, it shows you a diagram of silver versus aluminum. If you heat up silver, silver has a specific heat of 235, which means that energy is spread over fewer atoms, so it's going to gain more heat and quicker. That's why silver has a tendency to melt. So you can melt down silver very quickly, whereas aluminum has a higher specific heat. So you can still melt it, but it's going to take a lot more energy because you need more energy to spread over more atoms because they are smaller in size compared to your silver. So that's why they say these are heavy atoms, because they are bigger. So there are less of them to take up the same area as aluminum because aluminums are lighter or smaller. We can solve for heat equations and find out the amount of energy. This is the equation, so that you need to know the mass of the object, the specific heat of the material, and the change in the temperature of the material. So T1 is the starting temperature, and T2 is what the temperature ends as, the final temperature. So you find the difference, so the change in it, by subtracting them. Okay. And then you can find your amount of energy in joules. So here's an example problem. How much heat is needed to raise the temperature of a 250-liter hot tub from 20 degrees Celsius to 40 degrees Celsius? So we're looking for the amount of heat in joules. We know the volume is 250 liters, and 1 liter of water is equal to 1 kilogram of water, or 1 milliliter is equal to 1 gram. The temperature change is 20 degrees to 40 degrees, so that equals 20 degrees if you subtract the two. The specific heat of water, which will be a given to you when you're solving for these problems. And so you take the relationship, the equation, and you plug it in. So you figure out what your volume is, your specific heat, and your temperature difference. And you plug and chug and get your answer in joules. So you get 20,920,000 joules. That's a lot of energy. And again, it's because we have water. It has a high specific heat, so it takes a lot of energy to change that temperature.